Topic 20. Oh, wait, that's supposed to be topic 21. But anyway, we're going to talk about chi-squared real fast. And that's pronounced chi, not chai, like if you get chai tea. Uh, or key, which is what a certain game likes to call it, but it's actually chi. I don't know why they say that, but it's a chi-squared hypothesis test. I just had to mispronounce the word squared. Anyway, we're going to look at these chi-squared. Now, there's two types of chi-squared. The first one is called a goodness of fit. Goodness of fit test is used to see if the data fits well with normal trends of hypothesis tests. Now, you usually use this when you have a table of data, so you have kind of like multiple things fitting into your multiple categories fitting into one type of variable. So, which could fill out basically a one-way table like this. But example number 1, the American Red Cross reports that 42% of Americans have type O blood, 44% have type A blood, 10% have type B blood, and 4% have type AB blood. A county medical examiner hypothesizes the distribution AB blood types is the same in his country as it is nationally. A random sample of 200 people is selected, and the following data are tallied. Is the examiner correct? So basically, this is a chi-squared because chi-squared because we are looking at a table of values, and we basically want to see if they kind of jive with the normal trend that we see from American Red Cross. So things we want to do here. So again, just like everything else, it is a hypothesis test. So there are four steps in this. You have step 1, and it has its own condition. So it has what's called a counts condition, which just says that each category must be made up of counts, not percentages or anything similar. You have the independent condition that no category can depend on the other. And you have what's called the large enough data condition, where all data groups must have at least 5 data points. I know I'm making an error on that later, but I'll fix it when I get there. Now, a null hypothesis says is that all the categories are essentially the same as their expected counterparts. Alternate hypothesis, there exists one category that is different than their expected counterparts. So it works a little bit like this. I'm going to calculate, and then to calculate the p-value, it's going to be a little bit to it. But let me do the first 2 steps first, and then I will go to step 3 in a second. So, step 1 states this. So, if I look at step 1 for this one, what I'm going to say is that first off, I need step 1 is my condition. So number 1 counts. All of my categories are numbers, so they're all counts. So all categories contain counts and not percentages. 2. So my independence. Oh, man. My bad English strikes again. Independence. So basically, each blood category does not influence the other. Okay, and then 3. So large enough. Each category has at least 5. Okay, step 2. So basically in this case, for our hypothesis test, is we want to say that P1 is basically equal to 42%. P2 is equal to, which we can name them over here. So like P1, P2, P3, P4. So P2 is 0.44, P3 is 0.1, and P4 is 0.04. I'll put a 0 there just in case. And then the alternative is that at least one is different. Okay, so now I have that. Now to calculate my p-value here, just make sure all it's clear real fast. At least one is different. Okay, so calculating my p-value. So let me just go over this real fast. The null hypothesis is just basically you're saying they're equal to what the American Red Cross is saying. That's why we have these across like this. And then you're just saying here that at least one of them has to be different. The p-value for this is it's kind of complicated, but it's kind of not. First thing you have to do is find the expected counts, which we have to do anyway, which I'll show you in a second. Then you have to calculate for each category, you have to calculate the observed minus expected squared divided by the expected. And you have to sum all the results, and then you have to find the degrees of freedom, and then you have to find the p-value. You find the p-value from all of this, and you need to use a different graph, and so that means you have to use something other than the z-chart that I've been using that formulates this graph, and really it's just easier for us all if we just use a piece of software to do it for us. But you do have to do the expected counts. And what the expected counts is this. I know that there's 200 people. If I were to sum up this, it's 200 people. So I need to know what I should expect for each one based off of these percentages. So I need to do 0.42 times 200. I need to do 0.44 times 200. I need to do 0.10 times 200. I need 0.04 times 200. So if I do that, this gives me 84, 88, 20, and 8. So just add those up real quickly in my head. Wait, that might not be right. 12. No, that's right, because it's 20. Okay, good. That works. All right, so that's basically what we should expect if the actual blood types are right. So 42. If the blood type for A or O is really 42%, in 200 people, we should expect to have 84. If the blood type for A is correct, we should expect to have 88. For B, we should expect to have 20, and AB, we should expect to have 8. Which is interesting because AB is the universal recipient, so I guess it's just rare. I don't know. I'm not a nurse or anything, so I don't even know what my own blood type happens to be. But to calculate this in StatCrunch, we're going to go over to, first off, we need to go over here and create an observed, maybe spell it right, observed category. So the observed category, I'm just going to put all the data in from the table. Okay, and then we'll make an expected category. So it should be 84, 88, 20, and 8. Okay, so essentially what it's going to do is it's going to crunch some numbers, and it's going to let us know whether or not what we got represents what American Red Cross thinks should happen. So we're going to go to stat, and we're going to go down to this thing called goodness of fit. And we're going to chi-squared. Chi, not chai. Chi-squared. Okay? And so you need an observed column, which I conveniently tipped observed. And you need an expected column, which we'll talk about this idea when we have all cells in equal proportion in 1 second. We have an observed and expected. We don't need to press anything else, and we hit compute. And it tells us that the p-value is less than 1%. 1.0001. That's not less than 1%. It's actually far less than 1%. So we get step number 3. P-value is, we'll just call it 0.0001. Even though it's less than 0.001, we can just call it that because it's good enough. And then if we flip it back over, step number 4 is just the same as it always has been. 0.0001 is less than 0.05, so we reject the null. And in this case, what that means is that what the American Red Cross says isn't true. So we have enough evidence to show the percentages of the Red Cross are inaccurate. It's a goodness of fit test. It's inaccurate. This isn't the original thought process is inaccurate. We've shown it with our own proof. Now, just like always, with all of these tests, you can always have a type 1 and type 2 error. But I mean, with something that little, it's probably with the p-value 0.001, it's probably not going to be that inaccurate. Okay. So let's take a look at another one. So that's my example 1. Already talked about this. Second example, the concession manager at Twin Rivers Stadium wishes to see whether there is any preference in the flavors of popcorn that are sold during sporting events. Let me just reshuffle this real fast. A random sample of sales is selected and the data are shown below. Do the flavors have any equal frequencies? Now, you might see that there's no specific percentages with this one, and it all comes from the flavors have equal frequency. So the whole idea with this one is that all of the potato chips should be about equal to each other. So when we look at this one, first off, we're going to start all over again. We're going to get step number 1. So we have our counts. Every category is made of counts and not percentages. Basically, it's just not a relative frequency chart is what it's really saying. You can't really do anything with percentages in this particular test. 2, independent, all flavors. And now I am British because I put the U in there. All flavors are, oh, not are. All flavors do not influence each other. Basically, being a barbecue chip does not make something else a buttered chip. Oh wait, it's popcorn? Oh, it's popcorn. So I should stop saying popcorn. So being a barbecue popcorn is not the same, does not influence something to be a plain popcorn. Is basically what it says. My bad. I had was wondering why it was buttered chips. I was like, what is a buttered chip? What was I writing at this point? It's popcorn. Good. Okay, so large enough. So all categories are at least 5. Okay. Now in this case, it states they're all the same. So we can kind of write down for step number 2 for our null that P1 is equal to P2 is equal to P3 is equal to P4. And for our alternative, we just say at least one of these is different. Now again, we're going to go plug these into StatCrunch. And so, the fun thing about this one though is I don't need an expected column, and I'll show you why. So I plug these in real fast. Now the assumption is that they should all be equal. So when I go into my chi-squared, and I go stat, goodness of fits, chi-squared, I'm going to hit this observed, but I have this thing that says all cells is in equal proportion. So if I hit that, since my alternate hypothesis, or my null hypothesis is that they're all equal, I can just hit that, and that takes care of it for me. So I don't have to actually calculate what it would be to be equal. Although in this case, it would be something like, let's see, if I add them all together, I would get, let's see, so adding them together, I get 123, 25 plus 18 plus, oh no, I made a small error, small arithmetic error. It's 120, and I divided it by 4, so I could just as easily make an expected column where they're all 30, and that would still work, but, you know, I don't have to. So I get that, and I get a p-value of 0.0041. Okay. So step number 4. So 0.0041 is less than 0.05. So we reject the null hypothesis. We do not, oh sorry, we do, getting a little tired here. We do have enough evidence to show that the popcorn flavors are not equal. And there I went American for you. Okay. Alright, so they're not equal. Alright, so we got one more left. Well, then we got the second test to look at. So, third example. Staff member of an emergency medical service wishes to determine whether the number of accidents is equally distributed during the weeks. A week was selected at random, and the following data was obtained. There's enough evidence to reject the idea that the accidents is equally distributed throughout the week. So let's see if they are. So step number 1. So we have our counts. So all categories have counts and not percentages to so then we have counts, we have independence, 1 day does not influence the other days. Three, large enough, all categories have at least 5. Okay. Now once again, we're saying that all the days are the same. So say P1 is equal to P2 is equal to P3 is equal to P4 is equal to P5 is equal to P6 is equal to P7. I also sometimes just write down a sentence that says all the days are equal to each other, something like that, and then say at least one is different. So step number 3. So I'm going to go into my StatCrunch. And so let's see. Again, they're all equal, so I don't have to really make an expected column. I can if I want to, but I'm not really gonna. So I got 28, 32, 15, 14, 38, 43, and 19. Then we're going to go to goodness of fit, chi-squared. Observe, and then again, we want to test the fact if they're all equal or not. So we're going to click all cells are equal proportion, and then hit compute. And then I get something that's less than 0.001. So I go back and I say step number 4. So we reject the null hypothesis because 0.001 is less than 0.05. We have enough evidence to show that accidents accidents, I think it's that. Accidents, is it CE? Do I have to look it up? Yeah, that's fine. Accidents don't occur at the same rate on each day. Okay, so that's good. Alright, so we got one last thing to look at when it comes to chi-squared. Now this is mainly what I would test my students on, but there is one last one. But before we do that, when to use goodness of fit, the technical definition is use it when you are looking to see if there's a trend fitting previous or current trends. So, well, I said that wrong. Technical definition is that you use it when you're looking to see if data is fitting a previous or current trend. You know, like the data points are fitting the American Red Cross. Unofficially, you see if use it when there's one variable table of categorical data that doesn't involve percentages. And if it does involve percentages, you can just convert it over to counts. So it's really not that hard to do. But then we have this thing called chi-squared of homogeneity. And it's also referred to as the chi-squared of independence, because I've yet to figure out what the difference is between the two. So when I look at it, we need a two-way table, and honestly, I don't really do too much with this one, at least when it comes to tests. So my students don't really need to worry about it too much, but we will go over it. And it works like this. A sample of 200 components is selected from the output of a factory that uses three different machines to manufacture these components. Each component is the same. Each component in the sample is inspected to determine whether it is defective. The machine that produces the component is also recorded. The manager wishes to determine whether the relationship between the proportion of defectives and the machine. Manager wishes to determine whether there is a relationship between the proportion of defectives and the machine used. So we're going to have a very similar situation. Now, everything's pretty similar to what we did with the chi-squared test before. The only big thing is that it's a little bit different how you would calculate the p-value, but we're going to go ahead and just let StatCrunch do it anyway. But the actual calculations in StatCrunch are pretty terrible too. So, which is why I don't really use it that much, because I don't like to really torture my students. But we'll still go through at least one of these real fast, just so you can see what it's like. But it's still the exact same process. So step number 1. So you got counts. So all data is counts instead of percentages. We got independence. Now this one's really interesting because you're kind of already testing the independence between the two things. So that's not the independence you're saying. You're basically saying is that the categories, so the machine doesn't really affect the defects and vice versa. So you're basically saying each machine isn't affecting the other machines. Okay, and then we have our large enough. So each category has at least 5. Okay, so step 2. Yeah, this was a little bit wonky too. You kind of say that the defects are independent from the machine. Oh wait, I'm sorry, are not independent from the machine. And then here you say the defects are independent from the machine. Okay, now the weird thing about this one is how you're going to put it into StatCrunch. So When you go in here, first off, I need to get rid of all this. You are actually going to, and I want to get rid of that one too. So I'm going to put machine defective and non-defective. And I'm going to put, actually I have to put the A, the B, and the C in here. Oops. And then I have to put the 8, 6, and 12 in here. And I have to put the 54, the 62, and 58. And so now, to get this one, we're going to stat. Bear with me for a second because this one always kind of puts me off my... No, it's not that one. Okay, I think it's this one here. No, 1 second. I gotta actually, sorry. I just did this the other day and I don't know why I'm having issues forgetting it. It's tables, contingency. Is it this one here? Yes, okay. Stat, tables, contingency with data. And then your row variable is machine. Your column variable is both... Oh, wait a minute. This is not it. Oops. Okay, hold on 1 second. I hit the wrong thing. Okay, hold on. Stat. That's not it either. Stat. Just did this the other day. Why am I blanking on this? Hang on, I gotta find it again. Not that one, it's not that one. Not that one. It's not that one. It's not that one. This one here. Oh, I hit the wrong one, that's why. Okay, so I'll do it one more time. Stat tables, contingency with summary. You're gonna hit both of these. So you gotta hit control and click on both of them. And then your row variable will be machine. And then you hit compute. There we go. And so my p-value comes out to be 0.3479. Okay. And so with that, we step number 4, 0.3479 is greater than 0.05, so we reject the null hypothesis. We do not have enough evidence to show defects are independent from the machines, which means there's probably some kind of human error to it. So there's no real relationship between the two. Actually, that's a lie. I mean, there is a relationship. If they're not independent, then there is a relationship. All right. Okay. And honestly, I don't really stress this one too much. I don't really do it too much. Okay, last one. Example number 2. Suppose you take a random sample of 30 students who are using a new math test and a second sample of 30 students who are using the more traditional text. You compare students' achievement on the state test given to all students at the end of the course. Based on state test performance, would you recommend the new math book? Okay, so step number 1. So we got counts. So let's see. All data comes from counts, not percentages. Let's see. Independence. One book does not influence the other. And then actually, I'm going to go back real fast, because if I don't fix that, then it's invalid. So 25.5. So now, large enough, all are at least 5. Step number 2, null textbooks are not independent from grades. Hence, I'm gonna write a little thing here that when this happens, that grades are dependent on the textbook, meaning that if this option is true, the textbooks really are being, the textbooks are doing an influence on the actual grades themselves. Grades are dependent on the textbook. And here, textbooks are independent from grades. And again, that means that the grades would not be dependent on the textbook, which is pretty much what I would figure, because I usually don't like a lot of textbooks myself, but that's just me. So once again, I'm going to go back in here into StatGrunge, and hopefully I won't fumble around for 5 minutes trying to remember my way around it. So let's see. I've got go new, old, get rid of that. All this textbook. Got pass, fail, 25, no, 25, 5, 22, 9, delete. And so, stat tables contingency with summary. So I'm going to click on pass and fail, and then hit my textbook from a row. Hit compute, and I get a p-value of 0.2509. So we jump back. So 0.2509. Step number 4. So 0.2509 is greater than 0.05. So we fail. 1 second. Oh, my bad. Let me go back to this last one. I just realized I made a boo-boo. So we didn't reject. We fail to reject the null hypothesis. We do not have enough evidence to... I wrote everything else right. Now, I might even said we failed to reject, but I didn't write it correctly. So we failed to reject the null hypothesis in this one. And we also failed to reject. Failed to reject the null hypothesis here as well. We do not have enough evidence to say grades are independent of textbooks, so get the new textbook because it's failing less people. I mean, not by much, but it is what it is. All right.